to the pre-lecture video for Chapter 5. In this chapter, we're going to focus on normal approximation. And the center of normal approximation is something you're probably familiar with, the standard curve, or the bell-shaped curve. And the bell-shaped curve, as seen right here, is really a beautiful image, where you have just a bulk of data in the center, and then beautiful tails that taper off on either side. Now, what's so handy about the normal curve is that it's basically an idealized histogram. We just got through drawing histograms. So while one of our, more balanced and normal data sets might look something like this, with these blocks going down, that would be considered very normal data. What the bell-shaped curve, what our standard curve does is just curls out these edges a little bit to make it a little bit smoother and more beautiful. So a lot of data follows this pattern, as we've seen already. Your height and weight, when we've taken our own surveys, we've seen that the students' heights and weights follow the normal curve very well, that the majority of the class is within a certain range, and then there are the extremes on either side. ACT score and SAT score, those are determined based on where you fall on the normal curve. That the ACT score and SAT scores really are, they're standardized. So the scores are determined in a way that they get a result that looks just like this, where you have the bulk in the center and then very few high scores and then very few very low scores. So we see this all the time, and it's very handy and useful. So we want to get a little bit more comfortable in getting to use it. So the best part about the normal curve is that we're no longer going to have to take painstaking effort to drawing our own histograms. We're no longer going to have to look through every single data set and draw a histogram before we can make conclusions. If our data set is looking fairly normal, we can use the normal curve and assume that our data follows the normal curve very closely. So this is great. We are able to use just kind of a one-curve-fits-all data set for the rest of the course. So where do we even begin? Do we have to have a normal curve for shoe size when we want to look at shoes? Do we have to have a normal curve for ACT scores when we want to look at ACT scores? And the answer is no. We're able to apply any data set to the normal curve. But first, our data must be converted to something called standard units. So, what are standard units? Standard units are these numbers that we see at the bottom of our bell-shaped curve. Standard units are also referred to as z-scores. So we have standard units, which are called z-scores. And what this is basically a ranking of where you lie relative to your peers. It's unitless. It has no unit. It can be applied to anything. Height, weight, a GPA, your grade on the last exam you took, anything. Any data set can be converted into standard units, which is basically then your rank among your peers. How far above you are compared to the rest of the pack. So we're able to take this measuring stick and apply it to any data we want. So standard units, think of it as the standard measuring stick that we're able to convert out of units and into just this, this unitless measurement that applies to all different kinds of data. So if this is unitless, what do these numbers even represent? What would a z-score of 1 be, or a z-score of 2 or 3? Well, these are measured in standard deviations. So we see that we have, first of all, dead center in our curve, we have 0. 0 is the point at which we have half the data on the right and half the data on the left. This is going to be our average. So whatever we're looking at, let's think about it in terms of ACT scores. The average ACT score is dead center. You're the center of the pack, 50th percentile. Completely average, normal, dead center, z-score of 0. So what if you don't? What if you're not normal? What if you're not average? What if you're above average? Z-scores that are above average are these positive z-scores, all the positive numbers. So if you, and these are measured in standard deviations. So if you have a z-score of 1, that means that you are 1 standard deviation above average. And remember that standard deviation is unique to each data set. The only pieces of information that we need to be able to use this normal curve are the average, so that we can figure out what to put in the dead center of our curve, and the standard deviation, so that we know how thick each interval really should be. So those are measured, those are standard deviations. Now if you were below average on your ACT score, you would have a negative C-score, and that these are also measured in standard deviations, the distance you are away from the average in terms of standard deviations. So we're able to apply these standard units to basically come up with a rank for you among your peers, regardless of what the data set is that we're looking at. So this is going to be very handy because we're able to then determine what percentages of people lie between 2 points. And there's going to be some patterns that we see fairly often. Let's take a look. The most common ones are you're going to have memorized by the end of the class whether you like it or not, just because they're used so commonly. So if we have our normal curve, I'll try and, oh, that was pretty good. Here's our normal curve. We've got 0, a z-score of 1, z-score of 2, z-score of 3, -1, -2, -3. So the most common ones we see are the 1, 2, 3 rule. So if we were curious to see what percentage of the data falls between 2 points, we see that 68% of the data falls within 1 standard deviation of average in either direction. The second part of the rule is that 95% of the data, I'll draw it down here, 95% of the data lies within 2 standard deviations above or below the average. And the lesser known one is, oh, that's not exactly right, there we go, that between 3 and -3, within 3 standard deviations of average, we have 99.7% of the data. And that looks about right based on the locations on the curve. So, we could talk about this till I'm blue in the face, but there's nothing that's going to be able to show this to you like an example. So let's use some data that we collected from our very own survey. We asked you to tell us how old your mother is. And based on that, we were able to come up with some statistics. So how old is your mom? And we found that the average age was about 50, with a standard deviation, meaning the numbers typically deviated from the average, by 5 years. So 50 years old with a standard deviation of 5 years. So now if we were going to apply this to our normal curve, we have our normal curve, which again is in these unitless measurements. Oops, -1, -2, -3. So here in green, these are the z-scores. But in purple, down below, I'm going to make another axis, just to show you that these numbers truly mean something. So right at 0, a z-score of 0 means 50 years. So in purple, I'm going to say that this is relative to years. So a z-score of 1 would be 1 standard deviation above average. And what was the standard deviation for this data set? 5. So we're going to add 5 between a z-score of 0 and 1 to get 55. And we're going to do that same thing again for the next z-score. And we're going to get 60. And a z-score of 3 is going to be 65. And it works the exact same way in the other direction. If you have a z-score of -1, that means that you are -1 standard deviations from the average. So there's our average. You're subtracting 1 standard deviation, which is going to make your mother 45. And if you're 2 standard deviations below average, if you have a z-score of 2, we need to multiply our standard deviation by 2 to figure out how many years below average your mother is. So 2 standard deviations times 5 standard deviations will get you 10 years below average. So 40, because our average is 50. And there's 35. So you see that it goes in equal intervals of 5. So because our standard deviation is 5. So the main point we want to get across is that these standard units really do line up with true data. But whatever we're looking at, whatever kind of data we're looking at, we could have done pounds, we could have done your shoe size, we could have done your GPA, we could have done a lot of different things. So, but the best part is that standard units, it doesn't care. We can make any data set apply here, as long as it's somewhat normal. So, let's try and use this information to be able to get some useful statistics. My mother is 55 years old. So if I was curious to find out what percentage of mothers is my mom older than, I would hit up the normal curve. So the first thing we need to do, the golden rule of statistics, rule number 1, is convert to standard units. So convert to standard units. How do we convert to standard units? Convert to standard units. And remember, standard units are the same thing as z-scores, so we need to convert to a z-score. And so remember, before I was basically able to do this. I was taking z-scores and converting back to years to figure out, what does a z-score of 2 line up with. So we see that your z-score is basically how far away you are from the average in terms of standard units. So the first thing we need to do is determine how far away are you from the average. And then, because we want to become unitless, we're going to have to divide by whatever that standard deviation is to convert into SDs, basically. So this can be summarized in the formula, which is sometimes more hurtful than helpful because P students sometimes rely on formulas too much without understanding the concept. But the z-score formula is your value, how old my mom is, minus the average age for mothers, divided by the standard deviation of mothers' ages. So just once again, the top part, how far away you are from average in terms of years. Then we're going to divide by the standard deviation, which is also measured in years, so that you end up canceling the units out. So let's prove this. So I said my mom is 55 years old. So if I wanted to find my mother's z-score, I would say my mother is 55 years old. How far away is she from the average? Well, minus 50 years equals she is 5 years above average. But remember, this is a unitless curve, so I need to get rid of this unit. So in terms of standard deviations, how many standard deviations is she above average? She's 5 years above average, but how many standard deviations is that? Well, you can see logically that one standard deviation is 5 years. She's 5 years above average. That's going to be 1. But let's work this out with the math. We're going to divide by 5 standard but we're going to divide by the standard deviation, which is 5 years. So you see, years cancel out. We have years on the top and the bottom, resulting in a z-score of 5 divided by 5, which is 1, without any units, right? It's just 1. 1 that applies to anything. One standard unit, which is 1 standard deviation above average. So let's look at our normal curve now. If she is at a z-score of 1, that's where she is on the curve. This represents where my mother is on the curve. So there she is. Now remember, we had that 1, 2, 3 rule I talked about before, where we saw that between -1 and 1, we saw that 68% of the data lied there. And between z-scores of -2 and 2, we saw that 95% of the data fell between -2 and 2. And for -3 and 3, we saw that 99.7% fell in between those 2 points. And you might think I'm just pulling these numbers out of nowhere, but if you go to the back of your book, you're going to learn this in lecture too, there is a table that shows you, based on your z-score, what the area is between your z-score and the opposite z-score. So you can look them up in the table if you don't have them memorized. So the one that's the most pertinent, though, is 1 and -1, because my mother's z-score is 1. So first, find our z-score. Second, plot her on the curve. Third, plot the opposite z-score as well. So I'm just going to plot the -1, because we're interested in finding this middle area, the area between the two z-scores of interest. And the area between 1 and -1 is 68%. So 68% of mothers are within 5 years of average, meaning 68% of moms are between 45 and 55 years old. But remember, the question I was curious about was, what percentage of mothers is my mom older than? Not what percentage of mothers is she older than that are also older than 45, right? I want to have, who did she beat in terms of age, total. So the next thing we need to remember is from a little while ago that the entire normal curve, an entire histogram, always equals 100%. So if this entire histogram equals 100%, and now I've basically labeled the center of it as 68%, what does that leave for these equal tails? So 100 minus 68 gets me 32. So 32% is left over divided between these two equal tails. But I'm only interested in who my mom beat, right? In terms of age, who she's older than. I'm concerned with everybody who's lower than her. So I don't want this tail included. So I'm going to say 32 divided by 2 for each tail gets me 16% here and 16% here. So now all of the information is in front of us. We found our z-score, we plotted it on the curve, we looked up the middle area, we plotted our middle area, and then determined the areas of our tails based on the fact that all 3 sections of the curve have to equal 100%. Now that everything is there and labeled, it's a matter of reading our data. If this is my mom right here with a z-score of 1, the percentage of mothers who are younger than her, the percentage of mothers that my mom is older than, is 68% and 16%. So my mom is older than 68 plus 16% of mothers, which is 84% of mothers. So my mom is older than 84% of the mothers of Stat 100 students. So you can see that this is very useful, and it might seem a little complex at first, but this is going to be second nature to you very soon. It's so helpful to be able to forget units and just think about where you lie in the data in terms of ranking, which is all a z-score is. It's your rank among your peers, how far above or below average you are. So my mother is older than 84% of the moms. We'll keep that between you and me. I don't think she'd be happy to hear that. And I hope this has been a good introduction, and hopefully you feel a little bit more prepared as you enter lecture.